Thank you very much for giving me the opportunity to speak here. It's a wonderful place and a very interesting workshop. So today I want to talk about a topic that relates very much to what we've been hearing about last week. In particular, as an introduction, I would like to start from two lessons that we learned. Namely, from Nick's lecture, we learned that if we take a 3D n equals to 4 gauge theory, and by now most of people in the audience should, roughly speaking, know what we mean by this. We can view this as a 1D n equals to 4 supersymmetric quantum mechanics at low energies. Which is valued in what we might schematically call modular spaces of solutions to generalized vortex equations. So in particular, the 3n equals to 4 physics is very much related to the modular space of solutions to vortex equations. And the second lesson that is maybe more related to Oscar's lecture is that on a compact Riemann surface of genus G, which I take to be smooth, the solutions to vortex equations can be described by introducing some Hichiko-Bayashi type correspondences in terms of stable pairs. And I'm going to come back to this, but very schematically of E holomorphic vector bundle and some holomorphic section of it, smooth section that the equations require to be holomorphic. And this in particular can be then related to the algebraic, in the algebraic context, to stable quasi-maps. To symplectic quotients or stack quotients that I was talking a little bit more about, but that I'm not going to touch upon. So starting from these two lectures, today I want to illustrate a little bit what happens when we have less supersymmetry. In particular, I want to explain that if we take a 3D n equals to 2 gauge theory, this kind of theory is also displays some word crossing phenomena. When we talk about state counting. And furthermore, I want to claim that these kind of word crossing phenomena are related to the word crossing phenomena in vortex equations. So the one that I have mentioned there in an interesting way. So I want to relate this to Gaussian phenomena in vortex equations are in an interesting way related to this sort of problems. Okay, so as a quick introduction, I'm gonna briefly explain what happens in 3D n equals to abelian 3D n equals to 2 gauge theories. So for simplicity, I will start from theories that are labeled by the following data. I'm going to call them TK. They're going to have a gauge group U1. These are amongst the simplest theories that you can imagine. They're going to have some fields in the fundamental representations. And they're also labeled by a Chern-Simons level. That in this case, since for physicists I'm picking the field to have R charge 1, is going to be a half integer. In particular, I'm going to have a chiral field phi of R charge 1. And one interesting thing one can consider, or the first thing one ought to consider when picking some 3D supersymmetric theories, is to look at the vacuum equations. And these are a little bit different from the ones that we are used to in 3D n equals 4, in the sense that we're going to have other kinds of solutions that we weren't used to. In particular, for this very simple model, we can write the vacuum equations in the following way. Where I've introduced a real parameter tau, which is the Fi parameter Nick has been talking about in his lectures. And then they're modified by an effective, I'm going to have on this right-hand side something that depends on this scalar field sigma, it's a real field, and an effective Chern-Simons level. So sigma is a superpartner of gauge connections. It means that it kind of generates gauge transformations. And this K effective depends very much on the value of this real scalar sigma. And it's K plus 1/2 for sigma greater than 0, and K minus 1/2 for sigma lower than 0. So when people study these equations, they try to distinguish amongst 3 kinds of solutions. One are the Higgs solutions that Nick has also been talking about. So sigma is set to 0. Our chiral field needs to satisfy a moment Mach condition. And in particular, in this case, the gauge group is completely broken to the trivial group. We also have, for special values of tau, Coulomb branch solutions. These appear in this case when tau equals 0. And moreover, we require that K effective is also, that phi is also 0. And sigma is going to be arbitrary. So we're going to have non-compact directions in our modular space of vacuum. And third, we're going to have what I call, or what people call topological solutions or topological vacuum solutions, where phi is 0, sigma is equals to minus tau over k effective. And the gauge group is completely unbroken. So as a remark, we note that for the modulus case more than 1/2, there are no topological vacua. Sorry? Yes, tau is different from 0. Yes. And so we get a window in K where we have no topological vacua, and outside of which topological vacua start appearing. For the physicists in the audience, the effective theory around a topological vacuum looks a little bit like a Chern-Simons theory with the respective effective Chern-Simons level. For the more mathematically inclined audiences, it means that the model we're constructing will be governed by some sort of modular spaces of flat connections around that point. Having said that, what we want to look for is really what I'm going to be interested in is going to be the Witten index on a configuration that has this form here, S1 times a compact enumerative surface of genus G. So once again, we are going to have a supersymmetric quantum mechanics from the real line to field configurations on sigma G. And we would like to compute what is known as the Witten index, which Nick also introduced last week. And it's a graded trace graded by fermion number over the Hilbert space of this theory. So we are taking a trace in particular over the state of supersymmetric ground states, which are the only ones that contribute to this count. Yeah. Yes. Yeah, more generally, you can have larger windows. In this simple example, just ±1, where you have no topological vacuum. So here it's because I have one chiral of charge 1. More generally, if I have more chirals of more charges, stuff can appear here. Like I can have a n-half or something. And then the window where there are no topological vacua is larger. In this case, there are no topological vacua for k ±1/2. It's just that kappa effective is either 0, so you cannot divide by it, or it has the wrong sign with respect to sigma in order to solve that equation. Like the sign of sigma tells you whether it's +1/2 or -1/2. And so you have to have an alignment between where it's 0 and the sign of sigma. So if we want to compute such an index, I'm going to tell you what physicists do. We're following a long tradition. There are some techniques called localization techniques, which we are going to try to make sense of later from a more geometrical perspective. But so we can look at field configuration on sigma. In particular, the gauge field is the gauge bundle is going to have some topological degree that I'm calling M. In this case, the U1 theory. This M is just an integer. And So there are some supersymmetric localization formula that look a little bit like this. And as I said, I'm first giving you the result, and then we will try to make sense of it more geometrically. So it's a contour integral formula that receives several contributions. In particular, we are getting some classical contributions that come from the Chern-Simons levels, some one-loop contributions that are basically rational functions depending on the chiral fields. So these parameterized dx over x. And then a term that knows about the topology of the curve. So in this case, I'm just going to spell it out. It's going to be simply x to the power of km it's going to take this form here. So we have a nice integral that is for which we have a contour that I have to spell out. So my contour C tau depends on an auxiliary parameter. Usually it's valued in the dual of the Lie algebra. In this case, we can take it to be a real parameter. And it works as follows. I'm going to assign, so we have three kinds of poles in that expression there. We may have, depending on k, poles at, I mean, more generally, but poles at 0, infinity, or at 1. We're going to assign charges that look like this. We're going to, label the poles and assign some charges in this way. Q of 1 is 1. And importantly, if we're going to take this value here, if k plus minus effective is 0. So all poles have always assigned a non-zero charge, and the recipe is that I pick the residue at Q if eta at Qi, if eta Qi is greater than 0. So one consequence of this, which is interesting, is that if you look at what happens when the value of tau prime crosses the value of m, your counting is subject to our crossing phenomena. So let me define this. Let me define this to be tau prime. And we can compute that if tau prime goes from being a little greater than m to going a little smaller than m, sorry, let's say a little smaller to a little greater. Then the difference is going to be given by the following expression. So I'm going to call curly I am the integral and I am the integrand. So in particular, I can have word crossing only if some of my effective Chern-Simons level vanish. And well, this is the formula that comes out from this sort of localization procedures. And now our goal is try to make sense of this from the point of view of vortex geometry. Namely, we are going to try to localize our theory to some modular space of solutions to vortex equations. Sorry. Here I'm assigning 0 infinity, Q. Yeah, it's a label. For each pole, I'm assigning a charge. And I have a prescription that tells me which poles I have to pick in order to compute what I want to compute. So we have, what we want is to look for a vortex interpretation of this. I have to say that these sort of localization formulas, as already mentioned, have a long history. They go back to Nekrasov and Shatashvili, and they were then developed by several people. The formulas I'm using come from the papers of Kim and Closet from maybe 8 years ago, and Benin and Zaffaroni. And these modifications here, I worked out with some collaborators in a paper of 2020, where we carefully understood what's the role of these FI parameters in localization techniques is. And right. So I have a set of poles in my integrand, like at 0, infinity, and 1. Yes. Yes. And I'm like, when I compute this, when I want to compute the width and index in terms of the localization results, one of the things that comes out is a prescription for which poles I have to pick of the integrand. And in particular, I assign some charges to the poles, in this case, real valued. So K0 infinity gets this charge. According to this prescription, K1 is basically the gauge charge of the field. And then based on an auxiliary parameter eta, I'm just saying if eta pick all poles that satisfy these conditions, like eta times this real number is greater than 0. It's a selection of the poles. For more symplectically oriented people, it might remind you to the Jeffrey Kirwan prescription for in the computation of symplectic quotients. And this is not unrelated, but I'm not going to get into it now. Yeah, that's right. Kappa effective plus minus means that sigma is, I sent sigma to large infinity and minus to minus infinity. I should have mentioned it, if I haven't. So we can try to localize the configurations in our theory to something that looks like vortices. So the way to do it is very schematically, we take our Lagrangians. So we're going to have a term for the Yang-Mills term, that's the gauge connection. We're going to have a term depending on this tau parameter, tau deformation that I have inserted, a term for my chiral field, And then I can look at the configurations that dominate the tau goes to 0 limit. If you do that, you realize that you're going to end up with some principal bundle on the smooth curve sigma, some associated line bundle, which looks like this. And phi is going to be a smooth section of this associated line bundle. And sigma is going to be a smooth section of the adjoint bundle because the sigma field, as I said, lives in the adjoint representation. And by carefully taking that limit, you arrive at something that looks a little bit like the vortex equations, but not quite. And this is due to the presence of topological vacua. So in particular, the equations that we get on the curve, the time-independent configurations that dominate this path integral, look this way, look as follows. So we're going to have our standard expression for the vortex equations on sigma. But on the right-hand side, we're going to get a modification in terms of this real field here. So this guy here only exists when the effective Chern-Simons levels are not 0, which is a feature that only appears in 3D n equals to 2 theories rather than n equals 4. So it's a novel ingredient which is related to the existence of this topological vacua. These vortex equations are supplemented by the equations that we would expect and that we have seen last week several times, namely phi is actually a holomorphic section, not merely a smooth section. And moreover, the action of sigma on phi is 0. And remember that I am taking t goes to 0 here to get to this result. And so in particular here, if I want a final result, sigma needs to go to either plus or minus infinity. So these are the equations that I call generalize and say vortex equations that appear in 3D n equals to 2 theories. T is a localization parameter, which I'm taking to 0. Yes. So this is kind of funny. For people working with 3D n equals 4, you don't really see these things. But it implies some nice features. So let us look at what we may call the branches of solutions or saddles. Or equivalent to the saddles of the path integral. Well, sorry? Based on what? So far, I've told you, I've given you a formula that computes the weighted index. And from this formula here, I derived this result here. Yeah, so from this perspective, it just comes from the prescription for picking how I pick these things. So if k effective is 0, and I'm shifting tau to m, this guy is going to change sign. So I either pick it or not, depending on when it was positive or negative before. But I'm going to rederive that result if I have time, based on this more geometric framework. Yes, so yeah, I have my path integral, and usually you are interested in looking at what dominates at low energies. No, they are saddle equations. They're like the BPS equations. So I need to take it to 0. And now I'm going to talk about what happens. I mean, when I take this to 0, either this disappears or sigma goes to infinity, and this combination remains finite. So this is what I'm going to explain now. But if you compute the saddle equations, starting from your Lagrangians, it looks a little strange, but this is what you get. In particular, we have the standard vortex equations. So sigma is 0. So this term disappears completely. And I take my tau prime to be generic, meaning that I'm not hitting any integer m. But we don't only have vortex saddles, we also have topological saddles, which are related to the vacuum I was talking about before. Namely, in this case, my chiral field phi is 0. And the combination between sigma and t, remember I'm taking t to 0, remains finite. So in particular, sigma is bound to go to infinity. And in this case, I'm getting solutions that, well, you might still call them vortex equations if you like. We call them topological saddles, but they are solutions to these equations here, which are basically describe what Nuno might call dissolved vortices. So I have constant curvature and no chiral field contributing to the equations. Moreover, if tau prime hits one of the bed values and my effective Chern-Simons level, one of the effective Chern-Simons level, it's 0, then a non-compact Coulomb branch can open up. Meaning I have solutions for arbitrary sigma. Right. The condition of having the effective Chern-Simons level 0 may remind physicists that it is a signal that we have gauge neutral monopole operators. Therefore, when we hit these values, we might have a non-compact Coulomb branch that is spanned by the expectation values. Yes. Yes. Yeah. Yes. Yes. Yeah, I've simply integrated everything. There are only solutions if you satisfy this. So sigma 0 needs to be tuned so that you get this sort of solutions. If you integrate f, you're going to get this on the right-hand side. So the only solutions are where you get these things with constant curvature, having this value. So I've been tuning sigma 0. Yeah, that's right. For topological solutions, yes. And so So I'm gonna, if we call the, how much time have I got? 15 minutes? The modular space of solutions to my vortex equations. Let's call them star or what I expect is, as in any n equals to 2 supersymmetric quantum mechanics, is that roughly speaking, my Witten index is going to compute the holomorphic Euler characteristics of this modular space, valued in some bundle over it, depending on k, which I'm going to describe in more details in the example I've written down. So in this case, we have two components, disjoint components of the modular space for each degree m. One is a vortex component, and Nuno and others told us last week that it's basically parameterized by the symmetric product on the curve. Moreover, I have a component that parameterizes these topological symmetries. And I can try to describe them algebraically in terms of holomorphic line bundle on sigma, which means that this modular space of solutions is basically the picker stack of sigma. Now, picking a point of sigma, we might think about this as or a point on the picker variety. We might think of this as simply a torus 2G, where there is a sister action parameterizing automorphisms of the particular line bundle I picked that acts on it. So it's like a point mod C star times T to the 2G. So what happens now is that we can use some index theorems, or like the Hirzebruch-Riemann-Roch theorem, to express how these holomorphic characteristics look like on each branch of my modular space. So I'm going to have an expression for the vortex contribution. So I'm going to have the A hat genus of my modular space. No, it's the Picard of degree M. You might think of it as a torus, T2G torus. But in order to think about it as a Muth variety, I need to pick a point on it. And when I pick a point, I have to remember that there are automorphisms acting on the line bundle at that point. So it's really, I mean, a way of thinking about it is a point mod C star times azimuth 2G torus. I'm just keeping track of the automorphisms that act on this guy. And a convenient way to do so is to pick a point. And so on the vortex moduli space, I'm going to have an expression like this. I have to figure out what this line bundle is. It's going to be induced by the Chern-Simons term. And Chern-Simons terms have the tendency of introducing determinant line bundles on moduli spaces. So yeah, you can basically check that it's a determinant line bundle for lying over this moduli space here. But for the topological contributions, I'm going to have something similar. This time I have to remember two things. I'm still going to have a line bundle induced by my Chern-Simons term. It's basically the same thing as the one above, morally. But I also have to remember that I have massive fluctuations coming from my chiral multiplet that vanishes there, but have some massive normal fluctuations. And so I have to divide by the Chern character of this bundle here. So what is this bundle parameterizing my chiral multiplet? We can use technology that Nuno introduced. We parameterize line bundles on sigma and sigma. Over here we have a universal bundle. I have two projections. And one way to understand what this is just the derived push forward of my universal bundle tensored by the pullback of a square root of the canonical bundle, which is where my field was living. So in particular, if I restrict to a particular line bundle L, what I'm getting is an index bundle that encodes the modes of the field in L. Now, the nice thing is that the Coulomb branch result, this not motivated result that I wrote down earlier, is reproduced precisely by this sort of expressions here, if you go on and compute. And in particular, the residues at 0 of my integrand and the residue at infinity count topological contributions. Which I had circled in yellow. And one way of understanding this in a naive way, based on the amount of time I have, is that if I look at what happens when I integrate around 0 or infinity, I am basically picking things that are invariant with respect to that C star that I wrote over there. So my expression is going to look like this. I'm going to have an integral around 0 infinity of dx over x and an integral over 2g. So I'm integrating first over this torus 2g here, and then remembering that I have this action. Whereas the residue at 1 counts vortex contributions, pure vortex. And in the last 5 minutes, I will try to make a few remarks that will summarize the lesson that we learned and why, and maybe to note why these sort of things are interesting. So first of all, we learned that So the index can undergo word crossing. Provided my effective Chern-Simons levels are not zero. Sorry, are zero. Which means that at those points, a non-compact Coulomb branch opens up. Otherwise, we may have a change in vortex counts. But this is going to be compensated by a change of counts in topological vacua. So this word crossing that we derived is related to the word crossing phenomena for modular space of vortex as we knew them. The problem is that we are also counting other contributions that sometimes cancel them. And this is how index counts in 3D and equals to 2 theories work. So in particular, so in the absence of topological vacua, like in n equals to 4, my theory is going to compute simply the vortex contributions, which, as I told you, are these holomorphic Euler characteristics, with some determinant line bundles on top. And if you are familiar, at least a little bit, with quantum K theory, this might remind you about window phenomena that happen in quantum K theory. Observationally, the window where we have only vortex contributions correspond more or less to the window where people doing quantum K theory restrict themselves to. And but when you go outside of this window, the 3D theory doesn't like only vortices, but also likes dissolved vortices. So this count should be taken into account if you come from a physics perspective. Then, final two remarks. What I said can be generalized to non-abelian theories, but everything would have been just more complicated. In previous work, we reproduced in the presence of only vortex contributions the Hodge polynomials of rank 2 stable pairs using this sort of path integral arguments. And finally, if you're really interested in knowing what this 3D n equals to 2 theories count, ideally you would like to establish something like an Ichin-Kobayashi correspondence, meaning modular space of solutions to star go to some notion of stability of stable bundles on sigma G. And the presence of topological vacua seems to indicate that if we want to establish some correspondence like this, we need to allow maps or bundles or quasi-maps, let's say, to hit the unstable locus very often. In more vortex language, when we want to make this sort of counts, we need to allow vortices to dissolve when we have topological vacua. And this is more or less all I wanted to say.